Okay. Okay, so let us look at some issues pertaining to deterministic push-down automata. Just as a recap, let us note that a DPDA has some little bit different behavior than a PDA, which is non-deterministic by definition. First of all, for every input A in sigma and stack symbol capital A, and for every state P, there is a unique transition. And if there are no such transitions, then there must be a way out using an epsilon transition. And we will not allow a DPDA to ever halt or get stuck. And if the stack is empty, then any PDA, deterministic or not, essentially gets stuck. So we will never pop out this. Therefore, the stack is never empty. And therefore, the DPDA can accept only by final state. And I also assume that the input is terminated by a special end of input symbol, not in the input alphabet, which I denote by this. And the machine starts its working from the start state. This is the total input, the valid input X. I mean, this is over sigma star, in sigma star, followed by this end marker. And this bottom marker will always stay. Initially, this is the only content of the stack. If one or more transitions, the machine can reach a final state with everything read from the input, including this end of input marker. Then the machine is set to accept X. Okay. Whatever the content of the stack at that point is irrelevant. Only thing is that this is never popped out. So some gamma may be there on top of it. Doesn't matter. Okay. Okay, so this is how I define a deterministic push-down automaton. And now I define L, a language over sigma, is called a DCFL, deterministic context-free language, if here is the language of a DPDA M. Okay, so one thing is clear, except for some, I would say, different behavior, like the presence of this, which is not usually present in PDA. These deterministic machines can also be considered as non-deterministic, and therefore this is obvious, right? The class of deterministic context-free languages is content in the class of context-free languages. So is the other inclusion true? The answer is actually no. This is a proper inclusion, proper containment. That means essentially that deterministic push-down automata are inherently weaker with respect to language acceptance than the original non-deterministic push-down automata. Okay. So in the context of context-free languages, non-determinism imparts better language recognition power. So this has a role, non-determinism has a role to play. You have seen, for example, for finite automata, non-determinism can make certain, I would say, finite automata exponentially smaller in size in terms of the number of states. Okay. And here, non-determinism essentially gives better language recognition power. So this is good. And the question is why? How do I prove this? Okay. I will just give you a hint. This is an important theorem. I mean, proving this requires some time. I would prefer to avoid this complete formal proof, but I will give you an idea. Deterministic context-free languages are closed under complement. Okay. On the other hand, we know that context-free languages are not closed under complement, and therefore this theorem, if it can be proved, will imply that this is a proper subclass of this. Okay. Okay. So before going further, let us look at an example of a deterministic context-free language. So I consider this language A power n, B power n. Now what I will do, this sigma is definitely A comma B, but I will use a symbol capital A to count the number of A's, and then I will match that count with B's. This is the usual thing. And this is the bottom marker, which is never popped out. In addition to that, this stack uses a special symbol R standing for reject. Okay. If we see there is a problem in the input, this symbol R is pushed to the top of the stack, and after that, the machine will just enter a loop. Okay. So let's see what it does. Initially, if an A comes, capital A is pushed. If an A comes, when this capital A is on the top of the stack, another A is pushed. This is the usual thing. Then there is an epsilon transition. Note that here there is no transition marked by B. Or, yeah, B, right? So whenever a B comes, the machine has a unique way to do, that is by using this epsilon transition. Okay, without consuming B from the input. In that sense, it is deterministic. There is no transition marked by B here, this B, but there is a way out, that is by using this epsilon transition. Okay. And here, this is the normal behavior. Keep on reading keep on reading B, pop one A. So this is the normal. Acceptance loop, I would say. Acceptance procedure or whatever. Okay. So acceptance is perhaps not a good thing. This is a normal behavior that the machine should do. Otherwise, if something abnormal happens, the machine pushes an R to the top of the stack. So if for some reason some A has come, okay. So these two cases, some A has come where only B's are expected. So these two cases correspond to B after A. And therefore, these strings are not of the form A star B star. Then what it will do, it will keep the stack unchanged and it will push this reject symbol to the top of the stack. And this is a situation where the bottom marker is exposed and still another B has come. So there are more Bs. As of now, it's of the form A star B star, but the count of Bs is more than the count of A's recorded here. Okay. So this essentially means more Bs than A's. Okay. And this is a situation where the string is still of the form A star B star, but when this end of input is read, there are excess capital A's still in the stack. So that essentially implies more A's than B's. Okay. So these four are the situations. 1, 2, 3, 4. These are the situations where the machine should reject. And it does so by pushing this R to the top of the stack, keeping the stack otherwise intact. And whenever this R is there on the top of the stack, irrespective of whatever is there, if there may be something left in the input or not, it will enter this loop. Okay, so the loop of epsilon transitions. Read R, keep the stack unchanged, and so this is basically the reject loop. The machine never comes out of this loop if something bad like this happens. It never comes out of this loop and go to the accept state. On the other hand, if everything proceeds normally, so A's are read, as many A's are read, there is an exactly equal number of B's. Okay, and then end of input is reached, and at the same time the bottom marker is exposed. So the count of A's perfectly matches with the count of B's. In that case, it goes to the start accept state T. And of course, it is never allowed to stop there. So it will enter this loop. So I can call it the accept loop. So this construction proves that this language is deterministic, context free. Okay. So now, if I, yeah, tell. It seems to be some question.
Yes, sir. Sir, when this the second type of bottom marker is coming, and when the stack top is R, so we haven't considered that case, sir. Why, sir?
What?
This second bottom marker, sir.
No, this is, don't call it second bottom one. This is end of input.
Yes, sir. Sorry,
End
sir.
of
Sir,
input.
and when yes, sir. And the stack top is R.
Yes. We do
So
not
we
see
haven't considered.
we do not see a transition, but there is a way out. Do not consume it.
Okay.
Okay. So
Like
yeah, this is
yes,
the
sir.
point. If there is no such transition, there must be a unique way out by an epsilon transition. That is
Yes,
happening.
sir.
Okay.
Yes,
Good.
sir.
Good. So here also something I'm missing. B comma something. What should I do? Okay. This behavior is acceptable for a DPTA.
So the epsilon transition is chosen only if there is no transition labeled by that character.
Correct. Yes, exactly. There should be a way out. The machine cannot get stuck. Yeah, that is the reason. If nothing else matters or applies, we have to use such an epsilon transition. Okay. Okay. So now I briefly tell you how to proceed about proving this theorem. But an exact proof again involves a lot of, I would say, intricate details, which I would like to avoid because we should soon start our, I would say, coverage of Turing machines because not enough time is left. So, but only one I would say realization in this context is that switching final and non-final states does not prove the theorem. We have done this in the context of deterministic finite automata. If just simply switch the final and non-final state, and then that new machine accepts precisely the complement language. But this is not happening here. Okay. So for example, if I make this non-final, this one final and this one final, and you see that for every string of the form a power n, b power n, this will reject by going here. But if there is a string which is not in this language, then it has to be something like this: b after a, more b's than a's, more a's than b's. In either case, in each of these three cases, the machine essentially enters a loop, okay, by pushing R and then simply doing nothing. Okay. So unless we hit this case, okay, where the end of input is read, there is something else remaining in the input. Some A's, some B's, whatever. Okay. And even though this has been marked as a final state, the machine cannot take a decision, accept or reject decision, before consuming the entire input. That is by definition, right? It has to accept, after reading everything, the entire input string along with the end of string marker, end of input marker. This machine has chosen to reject by looping in this state without possibly reading the entire input. Therefore, you see that if I just make these two states final and this non-final, this machine is not going to accept the complement of L. Okay. So somehow I have to ensure that before rejecting, the entire input is read. Okay. So there are two things in the proof, actually. One, make a single reject state R. This R is reached after consuming, I would say, the entire input. Okay. And then it will keep on doing this loop. Okay. So I'll make a single reject state. Okay. So whenever there is a situation I want to reject, I will somehow read the remaining part of the input and go to the state R and enter this epsilon star by star loop. Okay. So this is one thing. And then if I just switch this T with R, make T reject and R accept, I can accept. This machine accepts exactly the complement of this language. Okay. So this thing is fine apparently, but the bigger question that arises in this context, how to detect the loops. I mean, premature reject loops. Okay, as it is happening here. Once R is there, it enters something like an infinite loop. Okay. Without ever consuming the remaining part of the input, including this end of string marker. Okay. So how to do that? This is perhaps an easier problem to solve, but this part is somewhat complicated. So I would suggest that if you are interested, you can look at our textbook where these two steps are clearly, I would say, explained. You can also look at previous year's video where you can find a proof. Okay, but what I will do, I will just make this construction for this machine. Okay. So situation, what is the bad situation? A or A this. Okay. A or A this. Keep the stack unchanged. Okay. Go to this, I would say semi-reject state. I am not pushing capital R or anything to the top of the stack. Instead, I am using this state R prime to remember that something bad has happened. Okay. Likewise, if I see an extra B whenever this thing is exposed, okay, I will also make the same transition to this R prime. The only utility of this R prime is I will consume the rest of the input if anything is available, keeping the stack unchanged. Star by star means whatever is there, keep it there. Okay. Read the remaining A's, read the remaining B's, if any. Then you read the end marker. Okay. End marker means end of input marker. Then you fall back to the state R. And you see that this situation, more A's than B's. This transition also reads this entire input. So if that thing happens, I will directly switch to this R. And there I will keep on looping. Okay. Now if I call this the reject state and this the accept state, then this machine will accept precisely the complement of L. Okay. So this is just an example, but this can be made to work in all cases. And that involves some intricate details, which I would like to avoid for the sake of time. Okay, so you finish the input, reading the remaining part of the input, go back to the new reject state, and then loop there. This is the basic idea behind this proof. Happy?
Yes, sir.
Okay, fine. If you're interested anyway, the book is there, previous year's video is there, so you can go ahead and check. Okay, so nice. I would like to mention some closure properties. Of deterministic context-free languages. Then I will stop. Then, of course, we have already seen, intuitively at least, closed under complement. What I will now show, deterministic context-free languages are not closed under union, intersection, and reverse. Okay. So maybe let us take intersection first. They are not closed. But you know, deterministic, the context-free languages are closed under union, but they're not, context-free languages, CFL are closed under union, but DCFL are not closed under union. So this is another difference anyway. So that's not an issue. Let's prove this. Okay, so with a little bit of, I would say, imagination, this language is context-free, right? Sorry, deterministic context-free. Okay. Now, if I just append some n, okay. So after reading exactly equally many m, a's and b's, you read some number of a's. M and n are independent. Okay. This is also going to be a context-free, deterministic context-free language. So you can design a PDA like this. Okay. Just consuming the remaining C's. Okay. So this is a DCFL. Likewise, initially you read some number of A's and then go ahead and match B's with C's. M and N are arbitrary. This is also deterministic context-free. But what is the intersection of these languages, of these two languages? It is A power n, C power n, and this is not even context-free, let alone being a deterministic context-free language. So this intersection of two deterministic context-free languages is not necessarily deterministic context-free. It may even be non-context-free. Okay, so deterministic context-free languages are not closed under intersection. I can do a similar construction. With a little bit of jugglery. Let's say A power I, B power J, C power K. I is not equal to J. And you can actually design a deterministic push-down automaton for this. Instead of matching I with J, I will force I and J must mismatch. Okay, and C power K, some arbitrary appending of any number of C's. And if I look at this language also, A power I, B power J, C power K, such that J is not equal to K, this is also deterministic context-free. And I take the union of these two deterministic context-free languages and call it L. Okay. So I assume that L is deterministic context-free. Okay. Then in particular, okay, deterministic context-free languages are closed under complement. So not L is, or complement of L is DCFL. And so SCFL. Okay. And if I intersect a context-free language with a regular language, I get again a context-free language. So it's something very similar to the product construction. Okay. The deterministic, the regular part does not require a stack. So the stack will be used for the context-free part of that pair. Okay. Therefore, I can say that this intersect with the regular language A star, B star, C star is a context-free language. Okay, but what is this language?
A power n, B power n, C power n.
Okay, but this is equal to A power n, B power n, C power n, and therefore this is a contradiction. Therefore, L cannot be deterministic context free. Okay. And the final example, reversal. Let us again look at this language. B, A power I, B power J, C power K, maybe I equal to J or I not equal to J, whatever. Consider this language. Okay. Now this is deterministic context free because if you read B first, then you know you have to match A's with B's. K is arbitrary. On the other hand, if you read C first, then you know you have to match J with K. I can be arbitrary. So you can take a deterministic decision at the beginning by looking at the symbol, first symbol that you read from the input. And if that is A, then you straight away go ahead and reject in whatever fashion by looping in a reject state or whatever. Okay. On the other hand, if the string is given to you in the reverse order, then what will happen? You have an inherent non-determinism. You have not yet seen the first symbol, which has now become the last symbol. Okay. Therefore, in the beginning, you do not simply know whether you are matching I with J or J with K. Okay. So that is intuitively the reason why this language is not deterministic context free. There are formal ways to prove that some languages are not deterministic context free. So there exist some specialized versions of pumping lemma. But anyway, these things are a little bit too advanced for this course. So if you want to formally establish that this language is the reverse of this language is not deterministic context free, then you have to use some such pumping lemma for deterministic context free languages. Okay, so I think we stop here. I stop here. Because an attempt to formally prove this important theorem will take another hour or so. I suggest that SK should take over and go into our next kind of machines, that is Turing machines. So if you have any questions about this deterministic context-free languages or anything related to that, let me know. And then, if not, I will hand over to SK. No? Okay. Then let me stop for the moment. Okay. So we are planning to have physical classes from next week, right? So does any one of you have any issue? So in the last week,
Sir,
you
the online classes would also run as usual, no, sir?
what is the question?
So means online and offline both will run simultaneously, or only offline classes will run?
No, currently the institute is going for what is called hybrid mode, with with the students that are already present, they will be in the class. We will use something like Blackboard teaching or some other mode of teaching like this, tab-based teaching in front of the students. And we have this Microsoft Teams that proceedings will be broadcast. So those who are not available will just join this Microsoft Teams.
Okay, sir.
This is what I understand. Anyway, we have to check that this equipment in the classrooms work perfectly. Without that, we cannot conduct it. That's up to us. We will check and let you know if there is a problem in the classrooms.
Sir, the tutorial on Thursday would be online or hybrid?
This week, let us continue as usual. Yeah.
Okay, sir.
Next week onward, let us do it. Yeah. Oh, there's another thing. So I hope we will be able to complete some one or two problems about DCFL and some other things in this tutorial. So maybe a couple of weeks after that. So not next week. Next week, let us have a test on these context-free languages. Maybe something like 45 minutes test or something like that. But you should have it. Otherwise, the syllabus will be too heavy for your final test. Okay. So maybe the tentative date can be 24th during the, let's say, tutorial hour. Okay, next week.
And so will these tests be online, offline? Which mode? Which mode will it be?
This thing depends upon how things go. I have heard that institute is mandating everybody to come back. It's now a mandate, no longer an option. So if everybody is here, we may have a physical test. And otherwise, we will take usual Google form based test. That depends on how things go. I am uncertain at this moment.
I think if you're on campus, then you have to be present physically for the test. And if you don't make it in campus, then you will probably submit it online.
Oh, that is the interpretation. Okay, okay.
I think that's how they are telling us to conduct the tests.
Okay. Okay, so we will let you know what exactly we should do.
So the ensems might be mandatorily offline. Is that a chance? Is there a chance?
I am hearing something like that, but no office order as of now came to me.
So, sir, can you tell us within this week? Because if that is the case, many people will have to travel back to campus within this week. So that
wait. This is not my decision. Whatever
okay,
the institute will decide, they will inform you.
Okay, sir.
As a teacher, I will just follow whatever they are telling us to do. Okay, so this is the duty of the institute. Okay.
Okay, sir.
Okay, so this mode and all these things we will let you know later, as soon as we are clear about this. So SK, you may start now, I believe.
Okay.
Yeah.
Just 1 minute. Can you see my screen?
Yes, ma'am.
Yes, ma'am.
Okay, so we will be starting with so far you have looked at two other kinds of models, the finite automata and the push-down automata. And Turing machine is considered to be like the ultimate machine model, where you capture what it means what it means for a function to be computable, or what it means for a problem to be computable. So this machine model was introduced by Alonzo Church around in the middle of the 20th century. And at that point of time, there were many other mathematicians as well as linguists who were trying to capture what does it mean to say what does effective computability mean. So several machine models were known. So here when I say machines, I actually mean machine models. So the computer, no form of computer existed at that point of time. There were several mathematical models that were being studied, and people wanted to know. So there were certain problems where you knew algorithms to find solutions, but people wanted to classify these problems. They wanted to know what does it mean for a problem to be computable. So far it was a case by case basis depending on the problem, and they wanted to find out whether there is a model, a machine model, that could capture the computability of such separate algorithms. And the Turing machine turned out to be one such model. Actually, there are many other models, and we will be looking at a few such equivalent machine models in terms of computability. We'll be looking at it probably in the next lecture or sometime next week. So we will also see why is this so strong. We will see that there is something called universality in Turing machines, which means that you can design or to start off, you can encode another Turing machine as part of input of a Turing machine. So you can think of this as you are designing this machine model where you're using another. So you can think of this, let's say you're looking at it as programs. You can think of it as a program trying to run a subroutine on some input. So Turing machines can capture this activity. So in particular, you can also design, which we will see later, you can design universal Turing machines, meaning that a machine that can simulate what, so let's say you have a particular Turing machine M, which takes in inputs. So you can simulate the actions of M on this input by another Turing machine. And you can do this for every such M. So therefore, you can think of it as a universal Turing machine where you don't have to specify which problem this machine is solving. You give me any problem, suppose that problem is solvable by some Turing machine, then you will be able to exactly simulate that particular Turing machine in this universal Turing machine. So as I said, you can think of it as a piece of Turing machines can do the following. So think of it as a piece of program that is being simulated on some input. This particular action can be done by Turing machines, and this will help us design universal Turing machines, where you can take another Turing machine as input, any other Turing machine as input, and simulate its actions on any input that particular Turing machine takes in. But we will also be using this particular fact of Turing machines to show that there are certain problems and the key feature of these problems will be they will try to be simulating some input machine, and these particular problems will be unsolvable by Turing machines themselves. So there is a sort of self-reference that is going on where a Turing machine is the problem itself has a part where you have to simulate the actions of some other Turing machine, and we will be maybe the same Turing machine itself, and then we will see that such problems are unsolvable in Turing machines. So all this will come later. So let's get into the description of what a Turing machine model is. So basically, this is a, so you can take inspiration. Yes.
Can you please zoom in a little bit?
Okay. 1 minute. Can you see it now?
Yes, sir.
Okay. So you will draw inspiration from all the previous machine models that you have seen, and this will be doing something much more powerful. So this will have more features than previous models. So in particular, first you have a single read-write tape, but it's bounded on one side. It's bounded on, let's say, the left side. It is infinite on the right side. So this looks similar to a stack. The difference between this and the stack is that you have a tape head that is pointing at some cell. So it doesn't have to be right at the end. So in a stack, you could think of, you could only read the topmost element of a stack. Here, you can move within this tape. I will be calling it a tape from now on. You can move within the tape, but the tape head pointing at the current cell can move in both directions, but at every step you move at most one step either to the left or to the right. And there is one other restriction, that you cannot move beyond the left end marker. There is a restriction to how much you can move on the left. On the right, you can move as much as possible. And in one step, the tape head moves exactly, the tape head moves one step, either to the left or to the right. So this is the classic definition of Turing machines. Then later on, we will probably see several other equivalent machine models that are very similar to Turing machines, but with added features. And the interesting thing is that we will see that no matter how many features you add, the computational power of those machines don't go up. Turing machines model is that robust. So there is the third feature, which was common in finite automata, push-down automatas, as well as in Turing machines, that there is a finite set of states, which we will be calling finite control. Okay, so Turing machine basically has these three components: a single read-write tape, which is infinite on the right and bounded on the left-hand side. So to mark the bound on the left-hand side, we put a left-end marker on the first cell, and this left-end marker should never be erased. No matter what happens, this left-hand marker stays. The second component is a tape head, which can move within the, which can move inside internal cells of the tape, and at every step it moves exactly one step either to the left or to the right. Third component is a set of states. Okay, now what are, so let's define it mathematically. So a Turing machine can be represented by this tuple. So what are the components of this tuple? Q denotes a finite set of states. Sigma is a finite set of symbols that represents the input alphabet. Gamma is a finite set of symbols that denotes the tape alphabet. So the alphabets that are written on the tape need not be alphabets that constitute the input string. But of course, sigma is a subset of gamma. We saw this extra symbol, which is a left-hand marker, which shows where the left-hand point of the tape is, and this is a symbol that is separate from, that is a tape symbol different from the the input symbols. So this belongs to gamma minus sigma. We also have a symbol a blank symbol which denotes something, which denotes, I'll just call it a blank symbol. You denote it either by this box or by this symbol. Okay, so that this just means that in this particular, if a cell contains this, then in that particular cell there is no non-trivial symbol. You can think of a blank symbol as a trivial symbol, and everything else in gamma is a non-trivial symbol. Then you have a transition function, which is defined on Q cross sigma. Notice that both Q and sigma are finite sets, and the output is a tuple belonging to Q cross sigma cross L comma R. Again, this is a finite set, so this is a finite, you can finitely define this transition function. And finally, you specify 3 states from Q. The first is a start state, second is an accept state, and third is a reject state. So the accept and reject states are 2 separate states. Either of them could be S, but T cannot be equal to R. And we specify them as accept and reject states. I will be coming to what it means to accept and reject. Okay, so first let's look at transitions. What does it mean to what do I mean by transitions? So at any particular point, if you're at a state P and you're reading A, your tape head is currently at a cell that has A written in it, then you will be using, then your transition function will be mapping P comma A to a tuple Q comma B comma D, where this is the significance of this tuple. Q is going to be the state you're transitioning to. B is going to be the symbol you're writing in the current tape cell, and D is going to be the direction in which your tape head is going to be moving. So pictorially, suppose your tape head is at some cell I which has A written in it, and in your finite control you are in the state P. Suppose you also have some state Q. Then after this transition, your tape your tape head, or let's say the ith cell will contain B, and your tape head, instead of pointing at the ith cell, let's say D is equal to L. Instead of pointing at the ith cell, will point at the I minus 1th cell. If D is equal to R, it will be pointing at the I plus 1th cell. And you will have made a transition from P to Q in the finite control. So this is the meaning of the transition. If you are at state A and if you are at state P and you are reading A at the cell that the tape head is pointing at, then the transition function is telling you what is the next state you are going to go into, what you are overwriting A with. It is possible that you're keeping A as it is. It is possible that A is equal to B, but what you are overwriting A with in the current cell that the tape head is at, and where the tape head is going to move, where the tape head is going to be before the next step starts. So whether it's going to move to the left or to the right. So this captures what the Turing machine is going to look like before the next transition happens. Okay, so one thing that we have to be careful about is, as I said before, that the left-hand marker never gets overwritten. We have to keep the left-hand marker as it is so that we don't move beyond the left-hand marker towards the left. For this, we need to ensure that if you have any P in state Q, and if you have any P in state Q, there must be some Q in some state Q such that if you are reading P, if your Turing machine is at state P and reading the left-hand marker, the transition function should definitely stay at the left hand marker and move right. This q could be equal to p, but there is some q such that you're always going to move right. The transition function is always going to make sure that your tape head moves to the right and does not override the left hand marker. So this is something that we have to ensure in the transition function. Another thing that we need to ensure in the transition function is that when I enter a state T or R, which corresponded to accept and reject respectively, when I enter these states, then you should not leave these states. Okay, so that basically means in my transition function, I ensure that you take any tape symbol B, there will exist some tape symbol C, C dash, D, D dash, which could come from left and right, such that if you are currently at the state T, the accept state T, and you're reading B, your transition function will make sure you stay in T, and then there is some C and D for the rest of the components. So you may be rewriting B by C, B could be equal to C, and you can be moving to the left or right on the tape, on the input tape. But you do not change the state. Similarly, if you are in state R, your transition function will ensure that you do not change the state. You could be rewriting on the current cell, and you could be moving your tape head either to the left or right, depending on what the transition function is. These two changes could happen, but the state does not change once you are in the reject state or in the accept state. The transition function is defined in, these are the two things that are necessary from a transition function of a Turing machine. Okay, so next we'll come to configurations similar to configurations that you've seen in push down automata. So at any point of time, notice that I will be having a semi-infinite string on the read-write tape. So a portion of it will be finite. So first thing will be a left-hand marker, and then there will be some y followed by all blank symbols. You can think of the tape initially containing only blank symbols, and then you add some, you rewrite with some non-trivial symbols. In however the Turing machine wants it, you may be writing some non-trivial symbols. So at any point of time, there will be a finite portion that comes from gamma star, and the rest of it can be thought of as having blank symbols. Now a configuration will basically be a tuple Q, from Q cross set of semi-infinite strings cross n, and this captures what the Turing machine looks like at this point of time. So suppose you have P, Z, N, then this basically means that currently you are in state P and the read-write tape has Z written in it, and the tape head is at the nth cell or the nth position of the read-write tape. So this is what the configuration captures. Now if we want to look at what the start configuration is on some input X, then the start configuration is unique. You will write down X. After the left-hand marker, you will write down X, the input. You are at start state S, and you will start off from the left-hand marker, which is the 0th cell. Okay, so when you're starting your Turing machine, this is what it looks like. You have the input string X written down and the rest of the cells have blank symbols, and your tape head is at this 0th cell, which contains the left-hand marker, and in your finite control, you are at state S, the start state S. This is your start configuration. So then automatically you want to find out what is the next configuration, and of course the next configuration will be something determined by the transition function. So the next configuration relation here is denoted by this right arrow, subscripted by the machine M, and superscripted by 1, denoting what is happening in one step, what is happening in the next step. So for a string Z in sigma star, gamma star, I'm going to define some notation before. Let Zn be the nth symbol. Okay, and I'm going to denote by SBNZ the string that is basically Z, except that Zn has been replaced by the alphabet B. Okay, at the nth position, whatever there was, I am replacing the nth element in Z by B. Okay, so if Zn was the nth element, nth symbol, I'm just forgetting Zn, replacing it by B, and the new string that I obtained from Z is SNBZ. Now, this is how we are going to define the next configuration. Suppose I am at state P and I am at the nth. So yeah, suppose I am at state P. My tape head is at the nth cell, and the transition function on P and Zn goes to state Q, rewrites Zn by B, and moves the tape head to the left. Then my next configuration will be as follows. From because I am at PZN, then my current configuration is PZ and my tape head is at the nth cell. And my next configuration is going to be by the transition function, P changes to Q, Z changes to SBNZ, because Zn I am replacing by B. So Z changes only at the nth position by B. And since the transition function asks the tape head to move to the left, then instead of pointing at the nth cell, it will be pointing at the n-1th cell. Similarly, if my transition function on P and Zn was QBR, meaning that I rewrite Zn by B, move to state Q, and move the tape head to the right, one step to the right, then the next configuration from PZN would be Q, SBNZ, and n+1. So this is how the next configuration is defined using the transition function. Now again, we can take the reflexive transitive closure of this of the next configuration relation to be denoted as right arrow M and star, denoting that there is some n such that you can derive the current configuration from some given configuration. And again, we will be defining it inductively. Suppose you are at some configuration alpha, then in 0 steps, you will remain in the same configuration. Suppose you are at some configuration alpha and you can derive the configuration beta in n+1 steps. It basically means that there is some configuration gamma which was derived from alpha in n steps, and then from gamma, beta is the next configuration. Some configuration beta can be derived from alpha if there is some n greater than or equal to 0 such that beta is derived from alpha in n steps. So these are things you have seen before. Okay, now let's come to acceptance and rejection. So Turing machine M accepts X if you can derive Tyn from the start configuration where T is the accept state. Y and N could be, Y is some string in sigma in gamma star, and N is some position on the read write tape. But the important thing is you are at the start state. You are at the accept state. So the set of such strings that are accepted by this Turing machine M is going to be denoted as L of M. And this is going to be the language accepted by the Turing machine. Now, what happens? What about the strings that the Turing machine rejects? A Turing machine is going to be rejecting X if you can derive a configuration of this form where the state is the reject state. Y and N could be Y could be some string from gamma star, and N could be some position on the read-write tape. But such a configuration can be derived from the start configuration. When I say such a configuration, I particularly mean that the state of this configuration is the reject state. So this is how I can define acceptance and rejection of strings by a Turing machine M. Now, we will say that a Turing machine halts on X if one of the two things happens. Either it accepts or it rejects X. But notice that it's not necessary that these are the only two outcomes on X. It is possible that the Turing machine enters a loop on the input X. So three things are possible. Either it accepts X, or it rejects X, or it inputs or it loops on the input X. So now let's go to some specific examples of Turing machines. So the first thing is, suppose I want to design a Turing machine that accepts even length strings. Okay, so notice that the language is a regular set. Accepting even length strings over some sigma. Accepting even length strings can be done by finite automata. You just have to check the parity of the strings. So can you do this with a Turing machine? The algorithm is quite simple actually. You are basically doing everything in the finite control, and you just have to make sure that you read through the string, read through the input string. And this is a transition function for this is a complete transition function for this problem. So I'll just say it in words. Look at the tape head. It starts from the left hand marker, and it will just keep moving to the right. As we move to the right, we will be storing the parity we've seen so far we will be remembering the parity we've seen so far in the finite control. So I think what I've done over here is this one denotes what happens if I read a symbol in the next step, and S denotes what happens. It's a start state as well as denoting. This S is a start state, and also this S and 1 denotes. So suppose I'm in the start state, then it denotes that I have read an even length string, substring. And if I'm at state 1, then so far I have read an odd length string. Okay, so in particular, if I am at state 1 and I am reading the first blank symbol, then including the blank symbol, so far I have read an odd length string. Therefore, I will be accepting such a string. And if I'm at state S, which sort of denotes so far I have read an even length string, including the blank symbol, so then I will be going to the reject state. So this one was pretty simple. You are basically remembering everything in the finite state, in the finite control. So next, we want to design a Turing machine that accepts a string if it is of odd length and the middle element is some special element, let's say a dollar symbol. So firstly, please check that this is not a regular set, but it can be a context-free language. Not a regular set mainly because you have to check what happens in the middle element. But you can design a context-free grammar for this quite easily. Please check this. This is not a difficult exercise. Now, basically to do this, First, you have to check whether it's an odd length string. Again, this is something that you can do in your finite control. Just take a pass through your read-write tape, and in your finite control, remember the parity of the string. The second step is finding the middle element. Once you find the middle element, you have to check whether it's this special symbol dollar or not. So second step is finding the middle element. And one way of doing this is you mark. So I'm just saying blue and red for these. So I'm going to replace my symbol. So suppose the symbol I'm reading that the tape head is reading at the moment is, let's say, A1. I'm going to replace it by something, A1 dash or something. For now I'm just saying A1 marked underlined by a blue underline. And similarly, I can also underline A1 with a red underline. Okay, these are the two things that I am using. These are the special markers. So if I have A1, I will also have if I have A1, I will also have this symbol, and I will also have this symbol. Okay. I mean, if I have A1 in sigma, then in gamma, I will also have A1 underlined by blue and A1 underlined by red. So what I do is look at the first element, first symbol unmarked by blue, not underlined by blue. So in the first case, I will see the first. In the first case, I will look at A1. So okay, so to start off, this is what it looks like, right? I have A1, A2 up to A7, and then I have the dollar symbol. No, sorry. I have A1, A2, A3, A5, A7. Then I have A6, and maybe again A1, A4, and so on. A6, A7, and then blank symbols. Okay, so to start off, after your you have your tape head at your left hand marker. Then in the next step, you move your tape head to the right. At the left hand marker, you are always going to move to the right. So you read A1, which is, so these are symbols from sigma. So you read you look at the first symbol from sigma, that is, you look at the first symbol from sigma, and you change that, you override that by its corresponding symbol that is underlined by blue. Okay, so you're basically underlining this symbol by blue. This and now you have to match this blue by something on the other side of dollar by marking it red. So basically I'm going to be counting I'm going to be matching the first element with the last element, and then the second element with the second last element, and so on. At some point I should be hitting a middle element. This is the idea of finding the middle element. How do I match the first element with the last element? Start from the left hand marker, look at the first element that is not underlined by blue. Underline it by blue. Now move to the right till you hit a blank symbol. Once you hit a blank symbol, move one step to the left till you hit a blank symbol, or you hit something that is underlined by red. Once you hit such a cell, move to the left, and in that cell you underline that element by red. So once you complete one marking of blue and one marking of red, you have matched these two elements. Now again you come back to the left hand marker, look at the first element that is unmarked by blue, mark it by blue, then move to the right till you hit an element which is marked by red or a blank symbol. once you hit such a symbol, you move one step to the left and mark the element in that cell by red. You keep doing this. So for every blue, I am trying to find a matching red. For every symbol underlined by blue, I'm trying to find a symbol underlined by red. Notice that at the center, you will have marked it by blue, but as soon as you move to the right, you will try to mark this as red. As soon as you move to the right, you should have marked, you will find that this is marked underlined by red, and you will move one step to the left and try to mark this blue underlined symbol by, you will try to underline this by red as well. This is when you know that this is the middle element. Now what remains is, once you have identified the middle element, what remains is to check whether it is the dollar symbol or not. And this checking, since sigma or gamma are finite sets, you can do this in your finite control as well. You can have a special state that checks whether whether the symbol red is a dollar symbol or not. If it is a dollar symbol, then you go into the accept state. Okay, any questions? So the idea was, first check whether it is a string of odd length. Second, you identify the middle element by take the leftmost unmarked, take the leftmost element that is not underlined by blue and the rightmost element that is not underlined by red. You're underlining them by blue and red respectively, so that they are the matching pairs. Then do the same for the again, you look at the leftmost and rightmost non-underlined symbols, mark the leftmost with blue, mark the rightmost with red. Keep doing this until you hit an element where you're trying to underline with blue and red. You're trying to mark the same element with blue as well as red. That is your middle element. Now the final thing is to check whether that middle element is this dollar symbol or not. Okay, so this is a brief sketch of the Turing machine. Yeah, I have also given the algorithm in words. The next example that we will look at is you want to design a Turing machine that writes a copy of the input string after the input string. So suppose X is the input string. At the end, your read-write tape should contain XX. So notice that this is not a decision problem, but I just wanted to show that these are things that a Turing machine can also do. If you want some operation, if you want a subroutine on X, this is also something that the Turing machine can do. This is how this is one algorithm. You can think of others. So basically what you're doing is on X, so you have the Turing machine. You have the Turing machine starting as follows. You have the left-hand marker and you have x1, x2 up to xn, and then you have the blank symbols. And the idea is that you have in your finite control, you have states that can remember which symbol I have read. Since sigma, gamma are all finite sets, you can do this in your finite control. You can remember the alphabet that you have read in your current cell in your finite control. So you look at the leftmost symbol after the left-hand marker that is unmarked. So to start off, x1 is an unmarked symbol. Now you remember this x1, mark x1, mark this thing, meaning that I am replacing this symbol x1 by a symbol from gamma, x1 dash, let's say, x1 underline underscore. Now you're remembering x1. So now you move your tape head to the right till you hit a blank symbol. When you hit a blank symbol, you rewrite this position. You rewrite blank by x1. And you can mark it in some manner, let's say x1 bar. You don't write it as x1, you mark it as x1 bar. Again, you come back to the left look at the first symbol that is unmarked. Notice that x1 is now marked. x1 has been replaced by a marked version of itself. So x2 will be the next thing that is unmarked. Remember x2 in your finite control, mark it. Now move to the right till you hit a blank symbol. Rewrite blank by x2 bar. You keep doing this, okay, till you don't have any unmarked symbols. So all the symbols are either marked by an underline or a bar, or they are blanks. So if you move from the left hand marker to the right, you do not find any you hit a blank symbol without finding any unmarked symbol. That is when you know you are done. Now what you do is, in one pass, you come back to the left hand marker. In one pass, if you have a symbol with an underline, you replace it by a non-underlined version of it. If you have a symbol with an overline, you replace it with a non-overlined version of it. Then notice at the end of it, you will have left hand marker followed by X, and then you have all the blank symbols. Okay, so this is a way. I have also written it down in words. This is a way you start off with X written on your tape, and you can write another version of it appended to X itself. Okay. Now let's look at another language. This language we have seen is a context-free language. Is not a context-free language, but we will design a Turing machine that accepts this language. A to the n, B to the n, C to the n. So just by looking at the language, can somebody suggest how to go about it? We've seen some ideas like how to mark alphabets and how to match things, how to match several alphabets, how to do counting, and so on.
Ma'am, we can take in the entire input first, and
Okay.
then we can match the number of A's with the number of B's using the underline and overline techniques.
Okay,
And then
so you have some X written down, and you're saying you are counting the number of A's. You're matching the number of A's with the number of B's.
Ma'am, first of all, we will check that if it's of the form A star, B star, C star.
Correct. So first you check whether it's of the form A star, B star, C star.
Now, if it is of the form A star, B star, C star.
Can you tell me how you check this?
Ma'am, this is a regular
Right.
set, right? So
Yeah, so you can use your finite control to do this.
Yes,
okay. Yeah. So okay. Now now suppose it's of the form A star, B star, C star. So you have some. Wait. So you have some IAs, JBs, and KCs. Now your suggestion is you match A's and B's to check whether I is equal to J, and then you can also match A's and C's to check whether I is equal to K, right? By this overline underline business. Yeah, got it. So
Then
this
when you say finite control, you mean that those states which
the
we are
states,
using?
yes, the set of states. The set of states I will also be referring in Turing machines. They are also referred to as finite control.
Okay, ma'am.
Okay, so let's go to another language which is not context free. This language WW. W is in sigma star. Can you design a Turing machine? So let's say I start off with X. Input string X. How do I determine? So first check is parity. First is parity check, of course. You check whether it's a even length string or not. After that,
And can we store the length of the string somewhere? and
Where?
then move those
Finding
many
the middle
steps.
element.
So whoever the first person who is length of the string, can you store the length of the string somewhere?
Then if we go from left to right, we can name every element, like if it's A, we'll call it A1. Then if the next element is B, we'll call it B2, something like that.
So
So in
what
the
will be
end, we
your
will have,
so what will be your tape? What will be the size of your tape alphabet? See, because ultimately when we are saying, when we are marking and stuff like that, we are basically using a tape alphabet, right? We are
yes,
not
ma'am.
marking just like that. Yeah.
It will be quite large.
It will be large. It won't be a finite set anymore.
Ma'am,
Yes.
if we can just, ma'am, for the parity check, if we use the underline overline method, so
Hmm.
if it is of even parity, we will have something like uh, the first half is underlined and the second half is overlined.
Okay, great.
And
Okay,
then
so
we can just,
you have some x1, x2. First half is underlined, second half is overlined. If it's even parity. If it's odd parity, anyway you are rejecting. So if it's even parity, your first half is underlined. So every symbol in the first half is underlined. Every symbol in the second half is overlined. Now what will you do?
ma'am, now we check if the first underlined symbol is same as the first overlined symbol, and then just make them remove the underlines and overlines and repeat.
How will you check if the first, how will you check that the ayat underline symbol is equal to the ayat overline symbol?
Ma'am, we can have states representing each of the alphabet, and
Right,
as that is
right,
finite.
right. Correct. So since gamma and sigma are finite, you can remember elements of sigma and gamma in your states. You design your state set in such a way that you can remember what you are reading, or maybe like some constantly many symbols that you have read, you can remember that in your finite state. Remember, in your finite state, we used to remember this fifth last element is 1. We can remember things like that in my finite state as well. So you remember what you are reading in your finite state, and then you match. So suppose you are checking whether the ayat underlined symbol is equal to the ayat overlined symbol. You read the ayat underlined symbol, move to the right, come to the ayat. So at every point, so you are assuming that everything before the ayat underlined symbol and has been unmarked. Everything before the ayat overlined symbol, all overline symbols before ayat overline symbol has been unmarked. So ayat underline symbol is the first underline symbol, and ayat overline symbol is the first overline symbol, and you have to check whether they have the same element or not. So at the ayat underline symbol, you remember what you have read, and you go to the first overline symbol, which will be the ayat overline symbol, and you check whether it's the same alphabet or not. If it's not, go to reject state. If it is, then unmark these two, and then go to the check for the I plus 1th underlined and overlined symbol. Okay, good. Any questions from others? Any questions? Okay, so let's look at another context-free language another language that is not context-free. A to the P such that P is prime. Okay, so I have it as follows. My input will just be PAs. Then blank symbols. So these are PAs. So maybe you saw something called Eratosthenes sieve, but that is Eratosthenes sieve is an algorithm where you determine whether a number is prime or not. So now can you design a Turing machine that accepts this language? Can somebody tell me what this Eratosthenes sieve method was?
We first eliminate all the multiples of 2 and then the remaining multiples of 3 and so on.
Right. Right. So if you have n, you write down everything. You write down 1 to n. And you forget 1. Now you cross off the multiples of 2. You just circle 2 and you cross off the multiples of 2. Then look at the next uncircled or uncrossed off number. So this is 3. Circle it and cross off its multiples. You keep doing this till n. So look at the circled numbers. These are the prime numbers from 1 to n. If n is circled, then n is also prime. So basically you have to do the same thing over here. How will you do it? So just basic, suppose I give you I, how will you, so suppose your tape head is at ith position. This is the ith cell. How will you mark off multiples of I?
We'll move left I times, then mark it.
Move
Then
left,
again,
so each of these you're saying you mark.
when we start from the second A, then we'll
Yeah,
mark.
okay. Start from the second day. Yeah.
Then we'll move. We know that we are at the second A, so we can move left by 2, then again by 2. We'll mark all those.
Left
Then,
or
oh,
right?
sorry, right. Sorry,
Okay.
right. Yes, right. Then we'll move back to the first element that is not circled or underlined. Then repeat
No,
the
but
process.
what do you mean by move by 2? How do you know? How will you know that you have counted till 2? Or how, at I, how do you know that you've counted till I? That was
I
my
don't
question
understand the
actually.
question.
See, you said 2, right? So how do you know so suppose you marked A and
Oh, right.
2. Now how do you know that the next thing, how do you know where to stop, where to mark?
Ma'am, we can,
Yes.
let's say we can enclose the A symbol in the ith position by 2 circles, and then
Okay.
mark everything that is to the left of the I, including that position, by 1 underline, and then we can just erase the first underline from the erase the first underline, and then append another underline after the last underline.
Okay, you erase the first and put a underline the next one. Now
Yes.
erase the second, underline the next one. Keep doing that.
Stop when we erase the underline from the double circle.
Double and
make
put it
it
as
single circle.
single circle. Okay. Okay, so what he is suggesting is you have, let me draw it again. So basically you cannot count. This is, if you have to count, even then you're sort of matching something. So you have, let's say A, so on, and you have the A at the ith position. Now my objective is to mark all A's that are multiples of I. So let's say this is 2I and so on. 2I and then you have 2I plus 1 and then you have blank symbol. Let's say this is how it looks. So what he is suggesting is, suppose I'm at ith position, I mark this A with double circle and then I underline all the A's till this A. Now I am basically going to be matching each element to the next element. Okay, so this is how I'm going to match. And every time I match, I sort of remove this underline to here. Then I remove this underline to here and so on till I match this one. When I match this, then I mark this with a single circle. So what this means is this double circle element is actually the prime number, and this single circle element are the multiples of this prime number. If at some point while doing these matching, so now once I get this, now I will have these things marked, right? I'll have these things marked, and now I will be again matching the marked symbols to the next thing. Now notice that at some point at the second A, I am matching it to a blank symbol, which means that I'm done. I have found all the multiples of this A. I have found all the multiples of I. Okay, so at some point, while doing this matching, if I run into a blank symbol, then I have found all the multiples of I have found and marked all the multiples of I up to n. Now what happens? After this, I have at each of these places, I have either marked, so I either have elements which are marked with double circles or elements which are marked with single circles. Now look at the first unmarked element and then continue. That will be the new, suppose the first unmarked element is at j. Now you start again, try to find all multiples of j. And okay, so one more step is required. At the end of finding all the elements, all the multiples of I, you mark this with a dash. Okay, which means that now, so now if in the next step, in the jth step, when you are marking with double circle and single circle, you know that these things, all the a dashes, these have already been processed. So that's why you also have to mark it with a dash so that you can come to the first element that is unmarked. And that is not a multiple of anything seen before. So there's just one more marking that was necessary. And at the end of it, when you reach a blank position without having come across any unmarked A's, then you know that you have marked all the A's either with a double circle or with a single circle. All the single circles are multiples of something, and all the double circles are primes. Now, if the last A is a double circle, then you know that it's a prime number. Then A to the P is such that P is a prime number. Okay, any questions? Okay, so to end things, I have just a few more minutes left. We saw a few examples of Turing machines. So basically, a Turing machine may accept, reject, or loop on an input string. And so far, I think the examples that we saw, I don't think we saw any examples where the Turing machine is looping. Yeah. So far, we haven't seen any examples where the Turing machine is looping, but it's possible. So it is going to be a Turing machine is called a total Turing machine if it is halting on all inputs, meaning that you give me any input, the Turing machine is either going to accept it or it's going to reject it. It's not going to loop on it. And a set of strings is said to be recursively enumerable if this set is the language of a Turing machine. It is called co-recursively enumerable if the complement is recursively enumerable, and it's called recursive if it's the language of a total Turing machine, meaning that it is accepted by so in this language is accepted by a Turing machine which has some more properties. All the strings, all the other strings, the strings in sigma star minus L are rejected by the Turing machine. There is no looping. So this language is going to be called recursive if there exists a Turing machine such that it accepts all strings in L and it rejects all other strings in sigma star minus L. It will be called recursively enumerable if the Turing machine accepts the strings in L, and on all other strings it might reject or it might loop. And finally, a property of strings on sigma star can be thought of as a language. So this is a subset of sigma star, and this property is said to be decidable if the set of strings that have this property P is a recursive set. So for example, all the languages that we saw before, the Turing machine for the Turing machine for the language WW was a total Turing machine. So this language WW is a recursive set, and I can think of it as this language having the property that it has a structural property of WW. So this property will be said to be decidable. This language is said to be a recursive set if it has a total Turing machine, and the structural property that this language has, in this case there is a structural property, this structural property will be said to be decidable. So similarly, any language, you can think of it as having some property, and that property will be said to be decidable, and the language will be said to be a recursive set if there is a total Turing machine that is accepting that language. And if that language is recursively enumerable, meaning that there is some Turing machine accepting this language, but the other strings, the strings that are not in the language, may be rejected, or there may be a loop on that string, then the property corresponding to that language is said to be semi-decidable. And yeah, so can you think of an example of a semi-decidable set? And we will be looking at examples of properties or of languages. So we will be looking at properties that are semi-decidable but not decidable, or in particular we will be looking at languages that are recursively enumerable but not recursive. So we will be looking at techniques to show that there exist languages which cannot have any total Turing machine. Okay, so that's the end of this lecture. Next lecture, we will be looking at equivalent models of Turing machines. So we will try to see what happens if we increase the power of Turing machines. So for example, a natural generalization would be, what if I had more than one read-write tape? I have one read-write tape in the classic example, in the classic definition. What if I had more than one read-write tape? Then can I solve more problems than the classic Turing machine? So similarly, yeah, we will be looking at other examples, and all of them will turn out to be equivalent to the Turing machine in terms of computability. Okay, thank you.